Okay, so we're going to start talking about 7.3 now. Before we do that, let's talk about what we did in 7.2. So what have we done so far? Previously, we can determine a basic feasible solution. We know that given m warehouses and n customers, or m sources and n sinks, we need m plus n minus 1 linearly independent variables for our array that's m by n. Okay, we have three ways of determining that initial BFS. Can you name them? Pause for a second, see if you can. They were Northwest Corner Rule, the minimum cost method, and Vogel's approximation method. Those were the three. Good. And so Northwest Corner Rule is probably the easiest, but it doesn't take any costs into account. Minimum cost method works pretty well. It's a little bit more work. Finally, the Vogel's method, VAM, takes a little bit more work, and hopefully we get a better initial BFS, right? That's the idea, is the more work you put into it, hopefully you get a better and better BFS. Okay, so then we can also formulate the transportation problem as a linear program. We can write its dual using UI VJA. The idea being these are our dual variables. UI is for the warehouse or source variables, the source constraints I should say, and the VJ will be for the customer or the sink constraints. We'll see that in just a second. Okay, so our goal today is to determine if a given BFS is optimal. If it's not optimal, find a better BFS. And hopefully that technique, we can just repeat our method until we solve the problem. Okay, so we're going to be using the modified distribution method, MODI, or just you can call it the UV method if you like. I think people tend to call it UV, but I see it defined as MODI in a lot of different places. So, all right. So let's start off with an example that we've looked at before. We have this tableau for a transportation problem, and I want you to write down the LP and its dual. So go ahead and take a moment, pause, and write down the linear program and the dual from this. Okay, so are you back? So here's the linear program. We're going to minimize the W equals, these are decision variables here. These two are the row sums and these three are the column sums. Let's go back and see. Right, so we have our constraints being the sum across, and then we have three sums down. And so we have 5 constraints altogether. Good. Now I'm going to you may not have put UI and VJ as your dual variables, but we should practice doing that. So like I said before, UI is going to be the variables for the warehouses, and VJ is going to be the variables for the customers. And so we'll have a U1 and a U2, and then a V1, V2, and V3. Okay, so if I use those for my variables, we see that we want to maximize 5U1 plus 2U2 plus 2V1 plus 3V2 plus 2V3. Okay, so that's our maximization problem. And our constraints, well, here you can see U1 plus V1 should be less than or equal to 3. U1 plus V2 is less than or equal to 7, and so on. And so there's our constraints. And notice that UI and VJ are unrestricted in sign. Why is that? Because we have equality constraints here. Very good. And so this is our original linear program, and this is our dual. Good. All right. So by complementary slackness, if the basic variable yij is greater than 0, what does that say about the corresponding slack variable in the dual? The slack variable in the dual is 0. What does that mean? That means that my inequality becomes an equality, and I'm able to solve an equality for the variables. Okay, so for the non-basic variables, I don't get that. I just have to be satisfied with the inequality. And so one thing you'll see when we're setting up these equations is that we have an extra variable. Why is that? Well, remember that how many variables do we have altogether? Do you remember? In general, you have m plus n variables, but do you have m plus n equations? We actually do have m plus n equations, right? We have 6 equations down here, um, but the problem is that the rank of the matrix is not that. The rank of the matrix is 4 in this case. It's the rank of the matrix is m plus n minus 1. And so if we have 5 equations and our equations have a rank of 4, that means we have a free variable. And so what we're going to do with that free variable is we're going to take our first variable u1 and we're just going to set it equal to 0, and that is a random choice. Okay, it's common to do that. Okay, so then given that, we should be able to solve for all the other ui and vj belonging to the basic variables. They must belong to basic variables. Okay, and then given that, we can compute this quantity Cij minus ui plus vj for all the non-basic variables, and that what we're doing there is we're computing the other values in the row 0 of the LP, and I'll let you think about why that would be. We'll prove that later on. For right now, we'll just try to we'll see that that works. Okay, and if those are all non-negative, if your row 0 in your linear program is all non-negative, then you know that the current solution is optimal. Very good. So here it is, our first example. We have a BFS, and our question is this BFS optimal? And so what we'll do is we'll compute our ui and vj first. So what did we say? u1 was going to be set to 0, and then this is, of course, this is telling us, right, that we have a basic variable here, and so 8 should be ui plus vj, and so that defines v1. Then v1 must be 8. If v1 is equal to 8 and this value is 9, these two should sum to 9, so therefore this defines u2, and u2 is equal to 1. And now if u2 is equal to 1 and the sum of ui and vj is equal to 12, that means this value is 11. Very good. Now I don't have any more from that column, so I go into this value, and now u2 is equal to 1. The sum should be 13. Therefore v3 should be 12. And if v3 is equal to 12 and the sum here is 16, therefore u3 is equal to 4. And if that's 4 and this is 5, that means v4 must be 1. Good. There we do. There we do. We have now computed all of our basic variables, or all of our ui and vj. Now let's compute the cells here for the non-basic variables, which we started here. That's the Cij minus the sum of ui plus vj, and so that's 14 minus 8 plus 4, so that's 14 minus 12 is 2. If we come up here, what's this value going to be? 6 minus 11, 6 minus 11 minus 5. Down here, 9 minus 15 minus 6. Up here, 10 minus 12 is minus 2. 9 minus 1 is 8, and then 7 minus 2 is equal to 5. Okay, so that gives us all of our values here, and notice that there are negative values here, so therefore this is not an optimal BFS. Down here I'm writing down the current value of our, this is actually W, not Z, but well, let's just call it Z so I don't have to make that correction on all the slides. Okay, so this is the current value of our cost. Good. Alright, so now how do I get a better cost? I'm trying to minimize this quantity, remember? So I'm going to take the negative value with the most negative and pivot in. I want this to become my new basic variable. So how am I going to do that? If I want to pivot this one in, what happens is I have created a loop. I have the linear dependence here, right? And so if I add theta, for example, here, then I have to subtract theta and add theta and subtract theta in order to keep my problem balanced. And so we can kind of see here these three values. This creates a loop. So again, if I put in theta, to keep things balanced, right, I have to add and subtract theta just like that. And so then the question is, how much can I increase or decrease theta by and stay balanced, right? It looks like this is going to be the defining equation here. I can increase theta by 10. Okay, and so one way to think about it is just to look at these four numbers, and if I increase theta by 10, that removes this as a basic variable, and so I have these numbers remaining, and these are my new set of basic variables. So let's go ahead and put that in, and this is my new BFS. And notice now that my z value just dropped by 60 units. Remember there was a -6 there, and I just increased that variable by 10, and the new value of z just dropped. Do you remember what that means? That means that the -6 was our shadow price. That was our shadow price. Our z value dropped by 60. Okay, I'm going to stop here and pick this up in the next talk, as we're about 11 minutes in. So you might think about what we just showed, and we'll continue the example here in the next slide. Oops, I hit the wrong button.